just quickly discussing like kind of doing recap of last class. So we started with a discussion on different types of machine learning tasks: supervised, unsupervised, semi-supervised, and reinforcement. Then like what are the frameworks of these for machine learning task types. Then we discussed like classification versus regression, particularly. Then we mentioned key what is linear regression. Linear regression is like given uh, x data point, like with the minute change in x, how much y is changing, and it assumes there is a linear relationship between x and y. Right? X can be multidimensional or unidimensional. Right? If it is unidimensional, it is simple linear regression. If it is multidimensional, it is multiple linear regression. Right, then we discuss the kind of squared, sum squared error, and what are the assumptions of this linear regression. So today also we'll go over some of these assumptions. Particularly, we'll use discuss these assumptions again. Homoscedasticity. What is homoscedasticity says? It's like error variance is constant across all levels of the predictor. So what do we mean by that? So this is the kind of mechanical error, while during the process of data collection, right? So this is kind of uniform across all data points, right? So that's what we discussed. Then we discussed like how to kind of estimate these parameters WB or whatever individually W through calculus. This is for univariate case, so there is extra B here. Then when we go to multivariate case, like kind of we fused B into the W vector by augmenting all one vector in the input X, right? Then in multivariate case, how do we compute this optimized W? We discussed that, and it gave us one closed form solution, right? And we discussed this loss function is also convex. So again, we'll discuss about convexity today also for logistic loss. So if you have any doubt regarding convex, you can ask me. Anyway, I am planning to discuss a little bit more about convex functions also. Okay, so this is what we proved why the sum squared error is convex. What we discussed is because the Hessian is greater than equal to 0, so meaning the Hessian matrix is positive semi-definite. If the Hessian matrix is positive semi-definite, that is the scenario for the function to be convex, right? So that's the theorem we used. And why this, what is the proof of this theorem? So that is beyond your syllabus. So just use this theorem, and every time we'll try to use this theorem to prove if the function is convex or not, right? So intuitively what you can think of is like, so if we have a curve, let's say this is our loss curve, right? Yeah, so if this is our loss curve, what the gradient gives us, gradient at any point gives us the tangent, right? Let's say at this point I'm computing the gradient, this will give us the tangent. For the so gradient meaning the like kind of the Jacobian in multivariate case, right? So what will the Hessian give us? Hessian will give us the curvature. So what is the curvature? So if curvature is upwards, like towards this direction, then Hessian will be positive. If the curvature is downward, like kind of let's say this is concave. The curvature is at any point. Curvature is downward, right? So curvature, if it is downward, it will give us negative value, the Hessian, right? So that's the intuitive explanation, but it requires rigorous math to prove it. So I'm just skipping it. Okay. Yeah. Then we discussed is this component in the kind of the parameter estimation of linear regression that is called the pseudo inverse of x, right? So instead of x inverse, because x inverse may be not a full rank matrix. Sorry, x may not be a full rank matrix, so x inverse may not be possible always. So we relied on the pseudo inverse, right? So we discussed when x inverse will be sufficient, when x in, like we need to compute the pseudo inverse, right? Then we again discussed the least regression using linear algebra, and we again came down to this same closed form solution, right? Then we discussed like, okay, so this closed form solution is nice, but it is computationally expensive. So how do we get rid of this time complexity? So if we perform the gradient descent. Gradient descent with accurate hyperparameter tuning, it can be faster than the closed form solution. right? Then we discussed about outliers. So how do we handle outliers? So instead of linear regression, we'll use ridge regression. Okay. So let me come to today's content directly. Then I'll come back to this outlier detection again. Okay. Sorry, not detection. Like kind of how do we handle the outliers in linear regression again. Okay. So yesterday we discussed majorly four class of tasks, right? Supervised, semi-supervised, unsupervised, and reinforcement. So apart from that classification, all the machine learning algorithms can be majorly classified into these two classes also. One is discriminative, one is generative. So what is discriminative? What is generative? So if you see these three graphs, so so these three plots, what's the first plot saying is original data, right? Some data points we have. So somehow we have got this data point, and it has two features, feature one and feature two. So we got this data point from some source. We want to kind of oversample this data. Like we have to sample more data from this distribution of feature one and feature two. So there we'll use something called generative models. So here I have used GMM, so Gaussian Mixture Model. There are more different types of generative models you can use to kind of recreate the distribution of the original data. So that's why they're called the generative model. We are generating data. What the discriminating model does, so it's like they have to do the task of discrimination. They have to create this like kind of hyperplane to segregate two classes or more than two classes, right? So that's the overall intuition behind these discriminative models and generative model, right? So this is theta, somehow got messed up, right? So so mathematically what we do in the generative model? So we compute the joint distribution of x and y, right? Given the data, like if the data is just x, right? So there is no y label, so we have to compute the like just the distribution of x. If the data has labels x and corresponding y labels, you have to compute the joint distribution of x and y, right? So if it has multiple labels, you have to compute the joint distribution of x, y1, y2, y3, or whatever the multiple labels are there, right? So how do we compute this? Again, we'll rely on the Bayes theorem, joint distribution. We can compute using Bayesian theorem, like x given y theta, and this is called the prior probability of y, right? So here we have to like kind of estimate two parameters, theta and pi. So pi is the kind of something called the class prior. If y exists in the given data, if y doesn't exist, you have to just compute the probability of x. Then this class prior will not come. If y exists, first parameter you have to estimate is the class prior. Again, you can use different estimation algorithms. So that we'll discuss next. What are the different estimation algorithms? So another parameter you have to estimate is theta, right? So what this theta looks like, you want to see like kind of what is the uh, distribution of x given the class level y, right? So what this particularly term called, we'll discuss next, right? So this is about generative method. So you want to estimate the joint distribution of x and y. In the discriminative method, on the other hand, what we are doing, so we want to directly predict y level given x, right? So direct mapping from x to y. So here only one parameter is involved, that is theta. So that is computed while this y level is predicted. So we discussed yesterday least square regression. So through least square regression, we are able to get this theta. We'll see different methods today. How do we get this theta in discriminative methods? Right. So here this table gives like a very broad overview of distinction between generative methods and discriminative methods based on multiple parameters. So objective in the generative is the joint distribution of x and y, and in discriminative it is just prediction of the conditional distribution of y given input data, right? So generative method helps in data generation. Discriminative method will never help in data generation. The assumptions like we have some prior in the generative method. Sometimes we assume there is some prior information we know. And discriminative method, we don't rely on any priors, right? So in using generative methods also, generative models also, we can do classification tasks. So maybe when we'll discuss the naive Bayes algorithm, we'll discuss that. But discriminative method, any discriminative method, by default they will do the classification task, right? Generative method also, each of the generative method can be used for the classification task, but the formulation will be different from the generation task. Right, so these are the major distinction between generative methods and the discriminative methods. So what are the like few examples of the generative methods? One is naive bias. Naive bias. One we saw in the plot, that is GMM, Gaussian Mixture Model. Um, so this decoder, the in recent days we are using the transformer models, right, in text, or we have these diffusion models in vision domain. So they can be used for as generative models. Discriminative, we have discussed one linear regression. We have discussed SBM. We are today discussing logistic regression. Then let's say decision tree. So there are many discriminative algorithms, right? And all the generative algorithms can be used for the discrimination task also. So this is something you need to know, right? So now coming to kind of the whole complete thorough discussions on the discriminative task. So for your syllabus, if possible, we will only discuss one like kind of generative algorithm, that is naive bias, and apart from that, we will only discuss the discriminative algorithms. So what is the formal definition of mathematical representation of a discriminative algorithm? So you are given some y labels for corresponding input data x, right? So always discriminative algorithm will have the y labels, whether it is supervised or unsupervised. So unsupervised also we don't know the y label for the training, but for verification at least we know the y labels, right? So what are the discrimination tasks, the task of the discriminative models? They have to learn this probability. What is the probability of assigning this input data x to particular class yi, right? So this is a generalized case of k class classification. Yesterday we only discussed regression. When we go to classification, we see binary classification and k class classification also, right? So if there are k classes, so you can, like I'm discussing about general case, you can kind of cut it down to binary case also. If there are k classes, how do we decide which class y belongs to, right? Because this discriminative model, what it gives us probability for assigning a particular x into y class, right? And this probability, if it is a probability, then it has to like obey all the properties of probability, like summation of all I probability of yi given x will be 1, and each probability will be greater than 0, right? So we know this property will hold. Now we have to decide which class this x belongs to. How we'll decide? We'll compare this thing. So if probability of assigning the particular data point into a particular class is higher than any other class, then we'll assign it to that particular whatever the class that has the highest probability, right? So that's how we'll make the decision during test time. So if you see here, so let's say this diagram, if you see, this is like kind of a representation of a discriminative model. So you have a two distribution, and let's say this is not actual classification between dogs and cats, because dogs and cats will have very high dimensional features because there are images, right? So let's represent this cats by these blue dots and these dogs by red dots, right? So what you can see here, the distribution of blue points are like kind of above this kind of hyperplane, and the red points are below this hyperplane. Similar things we discussed during SVM, right? Now you have to kind of separate, like learn this discriminative hyperplane between these two class. So once we learn this, we know if this is the equation of line, this is some like if it is in 2D, it is x plus by a plus c equal to 0, and we know if this is the equation of line x comma y. So what we can say, if x comma y, L of x comma y is greater than 0, this belongs to, let's say here, cats. If it is less than 0, it belongs to dogs, right? So this is how we'll make the decision, right? Then but how do we learn these things? So if you see here, so from this plot also you can assume, so this is what these contours represent. They represent the PDF of the uh, individual classes, right? This is the PDF of the dog, and this is the PDF of cat, right? So if you try to kind of plot this PDF, so this will look like this, right? So if you try to visualize from translational sides, not from the top side, so this they will look like this, right? So our target is to learn these distributions. So what is the mean of this distribution? What is the variance of this distribution? Once we learn this mean and variance of this distribution, that will help us to kind of learn, like kind of easily find this discriminating hyperplane, how to separate these two classes, right? So this, let's say for this class, whatever is mu1, whatever is sigma1 is the covariance, right? Or you can just say small sigma if it is unidimensional, or mu2, sigma2. These are the parameters. These are the parameters we want to learn, right? If distribution looks like this, right? Not always the distribution will look like this, but normal distribution is like the safest assumption. Using normal distribution, at least we can make some classifying decision, but not always possible, right? If two normal distributions are overlapping on lower dimensional case, how do we project it upper dimension, higher dimensional, and to make decision? We'll see that, right? So in K class, so if you see here, so this is also kind of another diagrammatic representation of how do we make decisions. So we learn, if we have K classes, model will learn parameters corresponding to each of the classes on the line, right? So yesterday we only discussed W transpose X, right? Yesterday we discussed till this point where W was a single column vector, right? It was having W1 to WP, and there is another bias term, right? So if there are multiple classes, we'll have to learn this W vector for each class. Once we learn the W vector for each class, let's say this is for some WC, this is for WD, this is for WH. So what you have to do, you have to multiply this X with each W, and see the whatever this the assumption is this will give us the probability, right? So actually this will not give us the probability. How we'll get the probability out of it, we'll discuss today. So assume this will give us the probability. Once this multiplication for with each of the classifier gives us the probability for assigning a data point into each class, then we will make the decision, right? So we are not learning only one W here. So overall, you can say the W is WC, WD, WH, W car again. So, but like there are four different W vectors. Apart, like as compared to yesterday, yesterday we had only one W vector. We have four W vectors in this scenario, right? So now the task is how do we learn these parameters, the W or mu or sigma, whatever the parameters are involved, how do we learn these parameters, right? So there are different parameter estimation methods, right? Yesterday we discussed one of these, that is least square regression, right? So we discussed this least square regression. So we're not going to discuss MOM or Bayesian or EM or like as part of discriminative methods. We only discuss MLE and MAP, right? Least square already we have discussed, right? These three will be our focus till end of your semester. So later you can discuss about MOE, Bayesian, EM on your own with your friends, or you can study this from other courses, right? So these points. I'm not going to discuss individually all these points. So when we'll discuss, we have already discussed the least square regression algorithm. So you see all the criterion and what are the points, if they're matching or not. If not, you can kind of ask me. So ML and map we'll discuss today. So in the end, maybe also in the next class, we'll revisit this table, particularly for these three columns, right? So these are the different parameter estimation methods. So we have discussed already LS. Let's start with MLE. So what is maximum likelihood estimation? So till now, any doubts on discrimination versus generation tasks? All good? Okay. So let's start with maximum likelihood estimation. So what's the maximum likelihood estimation tells us? It's likelihood is a term we know from Bayes theorem, right? So what Bayes theorem tells us, if we are trying to predict the posterior, that is probability of y given x, that is equivalent to saying a probability of x given y into probability of y by probability of x. Right? So we know this is posterior, this is likelihood, this is prior, this is like kind of total probability, right? So this is so from this definition we know this is likelihood. So what is this x and what is this y? X in machine learning setup is always data, input data, y is label. Okay. So then what is the like kind of intuitive goal of the maximum likelihood estimation? You have to estimate parameters that we like kind of increase the likelihood of x given the corresponding y level, right? So that's the intuitive definition of MLE, right? So what's the assumption we are having? So okay, so this has to be px x. The assumption is we are like kind of we have some given data distribution that is coming from this p of x, and this every data points from this distribution that we are sampling their IIDs, right? So IIDs like is kind of a major assumption in any machine learning algorithm because that helps in the optimization. Right? So now what do we want to learn? We want to learn parameter theta, so that will maximize the likelihood of maximize the likelihood of this px given y, right? So here if you see there is no y involved, so as I mentioned, sometimes we may have y in the input data or we may not have, right? Let's say the classic task of kind of learning like generating more faces for Indian cohort or American cohort. We don't have any specific y level, or let's say generating just faces, right? So there we don't have particular y level. We learn from like a bunch of faces across globe and how a face look like, and then we learn the like then we directly generate some new x that never exists. Right? Underlying there are some y level, so you can assume gender being on y level, or let's say a continent being country being on y level, but they are the latent variables. They are not explicitly given to the model. Model only sees the input x, that is the face, a bunch of face images, right? So in that scenario we don't have y level, so like I have given math like kind of representation for both scenarios. So if you don't have y level, you can write directly probability of x given theta, and so you have to kind of maximize this probability of x given theta. So what's the target? Target is you have to compute this theta star, that is r max of probability of x given theta, right? So in a way what it is doing, so we are given some, again this is p of x, yeah, so we are given some true distribution of the x, and we are estimating this x based on the theta. So if you see, this is the true estimation, like kind of the actual distribution of the data that is presented in through this PDF, a black color PDF, and this is red color PDF, right? The predicted distribution. So our target is to bring these two distribution as close as possible. If these two, like tail divergence between like kind of this whatever this pxx and px theta should be as low as possible, should be close to zero, right? So this is our target in the maximum likelihood estimation, right? So this is something again I have not discussed thoroughly as part of your kind of lecture slides. Again, I'm giving you a hint, you might expect some questions based on this concept. So like how do we kind of bring these two distributions close to each other using MLE formulation, right? So yesterday also we discussed 2-3 concepts from where you can expect some questions. So why I'm giving you these things, you will not exactly get those questions, but at least you should know which are the important concepts for every whatever the subtopic we're discussing, right? Um, uh, Mid-sem, many people could not answer the subjective questions, so it's just for all people in the classes. Everybody should come prepared. Okay, so very few people got like beyond 20 in mid-sem. Yeah. So now if we have the input data of the form x and y, so we have x level, sorry, x data point and y level also. So how do we kind of what is our goal? So we have to like kind of maximize this probability, right? Probability of x given y, right? So this likelihood we can represent through this formulation. So given data is this, we have to find theta that maximizes this likelihood. So what is this likelihood? Likelihood is like kind of the multiplication of these individual probabilities. So this I represents the individual data point, and this probability are like did I mess it up? Oh, sorry. Mm, oh, now it will not go away. Okay, so yeah, so the posterior probability is probability of x given theta, and this is likelihood is y given x, probability of x, like probability of right? So this is the likelihood you want to maximize. So if you don't have y label, we want to maximize only the x. If you have y label, we have to maximize this. This is the likelihood for us, right? This is the posterior. Sorry, this is not the posterior. So I will remove this when I will share the annotated files. Okay, uh, so if you understood how this multiplication is happening, so this multiplication is coming from this IID assumption. So because all data points are IIDs, so to compute the likelihood, we can just multiply them because they're independent from each other. And it's always in machine learning or in any probability, in any scenario where you are using probability, it's easy to compute, like convert all the probabilities into log form. Why? First thing is log is monotonic, right? So if you see the log plot, this is monotonic. So if there is a trend that is being followed in the probability space, same trend will follow in the corresponding logarithm space also. And by like converting this multiplication into summation, we can handle this numerical stability. So if you have multiplications, the multiplication can go down to 0 and there will be some floating point issues, right? So when we say likelihood, generally we consider only the log likelihood. So if you take the log of this likelihood function, it will convert the multiplication to sum. And this is our parameter estimation. So we want to maximize this log likelihood of the given input data, right? So that's the argmax of this kind of the log likelihood, and we have to get the theta that is maximizing this likelihood. Okay. So any doubt here in MLE setup? Right, so you have to know what is the likelihood of the data. So data likelihood is, because we're doing the discrimination task, we're doing the classification. Likelihood is like how likely this input data will be assigned to this class Y, right? So this, just ignore this part, particularly ignore. Okay, now let's see one example of MLE. How do we apply MLE to any input data points, right? So again, so when we're talking about the likelihood, so there is some assumption, like, so this probability of y given x comes from some distribution, right? So whatever the example I'm discussing today, all the examples will be discussing with the assumption that that distribution comes from Bernoulli. But again, you might expect some questions here. Instead of Bernoulli distribution, you might be asked with some other normal distribution or some beta distribution, something like that, right? So I hope you are familiar with the distribution functions. If you are not, let me know, because you are definitely getting a question on MLE with different distributions. Okay. Or if you are and you want to revisit those concepts, feel free to. Okay. So given data are coming from a Bernoulli distribution, x1 to xn, and we know what's the Bernoulli distribution. What is the PMF of Bernoulli? If we write its PMF, it is P if whatever xi is 1, otherwise it is 1 minus P if xi is 0, right? So this is the PMF of Bernoulli, we know, right? So only possible values are 0 or 1. You can consider coin toss scenario, 0 representing tail or 1 representing head, or vice versa. So what will be the likelihood? So here we don't have any y label, right? We are only given x, right? So how do we represent the kind of likelihood? Likelihood of this distribution is just kind of f of x, whatever the PMM for the PDF, right? This is what we have discussed. So now we represent the kind of PMF of the Bernoulli distribution. So we know from the given data point how many times 0 occurred, how many times 1 occurred, right? Number of times 0 occurred and number of times 1 occurred. So we'll use this frequency values to kind of get this likelihood, right? So we know what is this p-value for x being 1, then it occurred w times, and overall experiment was done n times, then it is n minus w times 1 minus p, right? So this we know from the distribution functions. So if you see here, so in ML, what we are doing, we are computing this like the occurrence, right? Number of times this 0 occurred, number of times this 1 occurred. So this computation of occurrences is something called frequentist approach. Frequentist. Right. So this MLE, so we discussed multiple estimation methods, right? MLE is a frequentist approach, and how it is different from MAP we'll discuss next, right? So LS also I'll compare in the end. So how in that way it is different from least square also, right? So MLE always rely on this frequentist approach. You have to compute on average how many times kind of whatever the particular distribution occurred. Right now, we have to maximize this kind of likelihood. So in that way, so to do that, what you have to do, you have to take the derivative and equate it to zero, right? And first thing is convert this likelihood to log form, log likelihood, then equate it to zero. You'll get so our parameter was p. So what's the kind of the correct estimation of this parameter? It's number of times the like kind of class 1 occurred with respect to number of times the experiment was done, right? So this we know already, right? So this is how we kind of estimate the parameter for a given data point, right? So you see the what is the underlying distribution. From the underlying distribution, we compute PMF or PDF, then convert into log likelihood, or then equate it to zero and compute the parameters, right? So that was MLE. Now let's come to MAP. So what MAP stands for? Maximum A Posteriori estimate, right? So here we are concerned about the posterior distribution, not the likelihood distribution, right? So if you see what is posterior, posterior is so what you have to maximize, you have to maximize theta, right? So this posterior formulation can be broken down into like this using Bayes theorem. It can broken down into probability of y given x theta, probability of theta. So here we discuss this as likelihood, and this as already prior, right? So now we have to maximize this term. To maximize this term, we have to maximize this and maximize this. So definitely we need to know the prior, right? So this is some extra condition we're adding to the kind of MLE. So in MLE, what we are doing, we're only maximizing the likelihood. In MAP, we're maximizing the likelihood, data likelihood, also the data prior, right? So let's go ahead. How do we like kind of maximize this MAP estimation using both MLE and prior? So yeah, so here if you see, so this posterior can be represented by likelihood, prior, and total probability. And this total probability is not, it's independent of theta, right? Independent of theta. So independent of model parameters. So you can completely ignore this. Now the likelihood of MAP can be represented by just the posterior and the prior. And this can be converted into some constancy. Right. So what's the goal? So what's the theta we have to kind of estimate? Whatever maximizes this formulation. So this we know already. Here log is removed because this log is already integrated into like likelihood of MLA, and this log p theta term is there, right? You have to maximize this and return the whatever the theta that maximizes this function, right? So this is what this is why I stopped at the outlier point discussion. So first we'll learn this what this title tells, then we'll go back to the like how do we handle this outlier points. So linear regression, the ordinary least square regression without any modification, without adding those lambda w null, is just called or like ordinary linear regression, right? Ordinary linear regression, instead of linear regression, we can write here OLS actually. Ordinary linear regression is done using MLE. Sorry, can be done using MLE. If ordinary linear regression is done using MLE, you just add the prior to it, it will get converted into Bayes regression. So the way the approach we applied for like kind of handling the outliers, right? So we saw this one, right? So this MLE term, whatever this maximizing this probability of y given x. So if you apply this formulation to compute MLE, then you just add the that extra lambda w parameter, it will get converted into MAP, right? So that is the end goal. So let's start with MAP estimation of linear regression problem, and how do we reach there, we'll see. For the linear regression problem, what we know, the given data is of this form, y equal to w transpose x plus some mechanical error. Okay, so that is coming from normal distribution 0 and sigma square, right? So now this likelihood, data likelihood, how we can represent. So this is normally distributed with parameter wx and sigma square, right? So you can write the normal distribution 1 by sigma into root over 2 pi to, or 2 e to the power not 2 to the power e to the power minus y minus double transpose x square by 2 sigma square. So this is common PDF of this normal distribution, you know. Now we have to do the map. So for map, MLE, I am not discussing how do we do MLE. So yesterday we discussed LS, like least square for linear regression. You can do also MLE also. Will like will reach at the same solution. So you can try on your own. Will reach at the same closed form solution. Right, I'm skipping the MLE of linear regression. So let's do the map of linear regression. So map estimate of the linear regression. For map estimate, you have to compute these parameters of the whatever the given machine learning setup, that is W, and the given data are XY. Right. So if you can easily convert into this joint distribution, right, XYW, and normalize by probability of XY, the total probability for XY. Right. So if you like kind of reshuffle and kind of convert into Bayesian form, you can rewrite this particular formula like this. Why? So this can be converted into probability of y given x comma w into probability of x comma w by uh, uh, yeah. So whatever it is, yeah. So just it can be written like this, right? You can break down this whatever the joint probability by probability of y given x comma w and into probability of x comma w, and numerator is probability of x comma y. Again, this distribution is completely independent of the parameter w that is used for the modeling. So we can completely ignore this term. That's why it is written proportional to not equal to. Right. So now again, what this term will be? So this term you can you keep the first term as it is, break down the second term. Second term can be broken down as probability of w into probability of x given w. Uh, uh, Once you like kind of break down this, you have three things, right? This was already there. That's the likelihood. Now probability of w, that is the prior we know, and there is this probability of x given w. Probability of x given w is again like kind of insignificant for us because x is the input data. We are not estimating the probability of x from the model parameter. It's rather opposite. We are try to estimate model parameter from the given data. So this is also something you can ignore, right? I'm ignoring it's in the multiplication step, but once you convert it into log space, it will be the addition. So you can ignore that because it will be some constant, right? Then final like log formulation of this map estimate will be log of pw given xy will be log of probability y given xw, that is MLE, then this prior log of the prior, right? So now we'll use that property of assumption of the linear regression, that is homoscedasticity. So, the error that comes, it's uniform for all data points, right? That's something. This error comes from this zero sigma square distribution, right? Normal distribution zero sigma square. This is uniform for all data points. So if it is uniform for all data points, so probability of w, let's write this. Let's write the probability by this formulation: normal of zero mean and 1 by lambda I. So why I'm able to write 1 by lambda I? So this is something you have to understand. This is constant for all data points, right? 1 by lambda for all data points. Everywhere else it is zero. So what is this lambda term? So this lambda term has some significance with the uh, uh, eigenvalues of whatever the input data matrix, right? So this is beyond the discussion of our course, so I'm ignoring this. So this the higher the lambda value, what will happen, like how the constant will be very stricter, and sorry, lower the lambda value makes the constant stricter. How do we? So all those things comes requires the discussion on eigenvalue, eigenvector. So that I'm skipping for now. Just assume. So this error, this mechanical error, comes from a zero mean and kind of same variance across all data points. right? So this is kind of a diagonal covariance matrix you can discuss, assume. So this is a covariance matrix. Covariance matrix for the error, mechanical error that we have. So that is a diagonal completely. Right. So how do we visualize the diagonal covariance matrix? So if it is diagonal covariance matrix, if you plot the PDF, so it will be concentric circles, right? If it is not diagonal, then it will be something like this, either this way or this way, right? So this is something you should know. Again, so all these things, the extra things I'm discussing might be helpful for you as part of your exam. But again, something in IIT or like this higher education, whenever you go in class, you will be studying something. In exam, you might expect something else. So that you are already habituated with. So expect that also. You cannot creep कि okay ये पढ़ाया नहीं थे class में. Yeah. So now coming to this maximizing this map estimation. Now how we'll get this W value, right? So you have to maximize this whatever the log of the map estimation. Now this we know what is the distribution of this whatever the likelihood. We already got this. This is normal distributed with this parameter that we can write like this. Once you break it, it will create these two terms: log of 1 by sigma 2 pi root over and log of this. Now this is something of our interest, right? So what is this log of P of W? P of W is mean 0 and covariance matrix is this 1 by lambda I. So if you write like kind of write the PDF of this, it will be like just e to the power minus W minus 0 transpose sigma inverse W. Right here again, what will be the sigma inverse? Because sigma is 1 by all diagonal 1 by lambda. So sigma will be sigma inverse will be just lambda, 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 all diagonals, right? Everywhere else 0, right? This is because this is a diagonal matrix, right? And now we have a very nice part. So now if you kind of, it's log of exponentials, you can easily take them outside. Then it will be lambda into W norm square, right? The W transpose and W transpose is there, and this is a scalar. So this I'm writing for each data point. So this formulation is for the complete data set. That's why it is W transpose sigma W. Now, if you write into individual data points, so this sigma will convert it into this individual lambda, right? And we can write W norm square, right? Now, if you see, so this is our kind of the likelihood of the map, and our target was to maximize this likelihood, right? Maximize this likelihood LW. In a way, we have to minimize the negative of this. If you try to convert it, like take the negative of it, so this minus will go away, this minus will go away. This is the kind of the minimization formulation. Argmin of W, y minus W transpose x square by 2 sigma square was there plus lambda W square. So sigma square we just removed with some assumptions, sigma being 1. Again, this is for mathematical convenience, but it can be something else also. Right now, if you see this formulation, W star equal to whatever this happened, this is exactly what we are doing in the ridge regression last class, right? So not using this formulation, using some other formulation, we like we came down to this formulation in the ridge regression yesterday also, right? So if you go to ridge regression, right? So this is what we said yesterday. So only there is one constant term that is divided here. This constant term, again, you can find if you are taking the mean square error instead of sum square error, right? So that constant term you can ignore. So apart from that, exactly same formulation we got using the map, right? So why it is able to help kind of again handling the outliers. So what will happen? So if there are outliers, where is the formulation? Yeah. So if there are outliers, so for outlier points, if even if it is the assumption is homoscedasticity, so outlier points we can have different lambda values. So this is the so when we are like kind of doing optimization problems, we'll start with many assumptions, but in real life those assumptions will not hold always. Like 100% of times, whatever the assumptions we start with, unless that is a very strict assumption, those assumptions will not hold. So similarly here, the homoscedasticity assumptions will not always hold. If it will not hold, So this lambda value you can kind of consider as hyperparameter, and you can change it. Once you change it, you can control how much weightage you are giving to each W. And what is the W? W is associated with corresponding Xi, right? If some Xi is outlier and corresponding W is very small, it's kind of you are kind of diminishing the effect of those outliers, right? So that's what model will learn automatically, right? So this is kind of all like kind of combined picture of MLE and map. A map we are not going to discuss anymore. This is just the single discussion on map. All the algorithms will only discuss the MLEs. Okay. So any doubt till now for MLE or map? Okay. So if not, let's go ahead into logistic regression. So yesterday we discussed linear regression, and it was like, okay, the assumption was the relationship between input and output are kind of linear in nature. So what is the assumption in logistic regression? Logistic regression, there is no such assumption. And it's by name, it is regression, but it's not a regression task. It's a classification task, right? So why they gave regression name? So that there is some significance to it. So we'll discuss once we see what logistic regression is doing, right? So this is a classification task, and it uses some function that is called logistic function, right? So that's why it is called logistic regression. Um, and why the logistic name came from, where the logistic name came from? It came from the odds ratio. So what is odds ratio? If you know how the gambling works in any sports or anything, so let's say I know for India to win the final, India has like kind of likelihood of let's say whatever which was our opponent yesterday's final, India versus Australia, that whatever Masters week was going on, India versus West Indies, sorry. West Indies has like kind of likelihood of 1 is to, let's say, 4 for India, in favor of India. So what's the odds? Odds is like, these are the likelihood, right? So what will be odds? Odds will be a kind of whatever was the likelihood by a whatever is the highest likelihood minus the least likelihood. This is the odds. This is how odds are computed, right? So how do we say this then? So originally I was saying, okay, India has like chance like let's say 88% chance of winning, and West Indies has 20% chance of winning, right? What is the odds for India and West Indies? The odds for India will be sorry, something is going away. Let's compute the odds for West Indies first. Odds for West Indies will be 1/3. Then odds for India will be 2/3. So, like when gambling happens, they compute the odds like this. They don't compute the odds like from the percentages directly. So they compute odds like this, right? So that's something called the odds ratio. And which distribution captures this odds ratio, which functions capture this odds ratio, is the logistic function. How logistic function captures the odds ratio? If you represent this p my 1/p into some x plus b for, what this says, with unit change in x, how your odds are changing, right? Yesterday we were discussing y equal to w transpose x plus b, right? There we are discussing with unit change in x how b is changing. So here we are discussing with unit change in x how this particular odds is changing, not any single element y or p, right? So particular how the odds get affected with unit change in x. So this relation is being captured easily through the logistic function. What is the logistic function? Logistic function of, let's say, logistic, sorry, not the logistic function. Okay, logistic function or the sigmoid function, the same synonymous name. Sigmoid of x is something 1/1 plus e to the power minus x, right? So if you kind of so this is not p by 1/p log. So the odds ratio tells with unit change in x how the log odd change, how much the log odd change, not just the log, is not just the odd, right? So you take exponential each side, you will reach at this formulation. So this formulation, this function captures this relationship with unit change in x, how much this log odd changes. So that's why the name sigmoid logistic function or the sigmoid function came. Okay. So this is yeah. So this is So this is the significance of the logistic name. Now we'll see what in this classification task what we are doing. So for the classification task, you have to make some decision, right? Like given x, whether this x belongs to class 1 or class 2, right? So if you have two class scenario, so why can't we just compute W transpose X like linear regression and make the decision, right? We can do that. We can do that, but it's not kind of physically significant. What do I mean by being physically significant? Where do we have space? Right. Let's say if you have multi-class scenario, dog versus cat versus house versus car, right? So what linear regression will do? So what do you do? So you represent these individual classes by some number 0, 1, 2, 3, right? Because like machines only understand numbers. So linear regression will assume it will not capture the difference between dog versus cat semantically, right? So it just consider this as 0, this is as 1, this is 1, this is 2. It's not capture the semantic difference between cat versus house, dog versus cat, right? So to get the semantic difference, you need to convert them into not 0, 1 labels as such. You have to get the probability of dog, probability of cat. So you have to project them into probability space. So which function can help us to get into probability space? That's the sigmoid function. How sigmoid function helps us to get into probability space? So let's get into this plot now. So given my data point from minus infinity to infinity, what the sigmoid function does? So sigmoid function is this, right? 1 by 1 plus e to the power minus z. What sigmoid function does? It squeezes down everything into 0 to 1, right? This is the y level, right? And this is the kind of criteria for probability, everything summing up to 1, everything between 0 to 1, right? So all like kind of the x values between minus infinity to infinity can be squeezed down to 0 to 1 y values, right? So that's what we wanted. The probability should, so whatever, instead of presenting them through 0, 1, 2, 3 class names, so we can present them through some probability values. And sigmoid function can do that. So that's why for classification, we can't use, even if we can use linear regression, but we don't use because we need the probabilities, right? So now how we'll convert that linear regression formulation to kind of this probability formulation. So this is Bernoulli, right? So what do we do? So I think, so class is still 10:25, right? Or 10. Okay, so logistic regression maybe we'll continue next class.